right, thanks, Dudley, and thanks everybody for joining us. So today I'm going to talk about how construction damage impacts trees, and then how trees that have had construction damage are impacted by severe storms, and then we'll kind of wrap up with some potential solutions or things to think about when working around trees, and street trees in particular. So when I say construction damage, I'm really talking about sidewalk construction damage. Both of the two projects and research that I'm going to focus on today really looked at how trees interact when we have sidewalk damage in our urban areas. So here's a tree. This is actually in Minneapolis, where I was working prior to coming to Nebraska. And you can see that the sidewalk has been newly replaced. This is right by an elementary school where the school had been being redeveloped. And you can see that basically they gave the tree a little extra room, which on the face of it seems pretty nice until we look at how they did that, right? So this is the root that was essentially severed, and that's my helmet next to it, so you can really get a sense of the size of the roots that are often severed when new sidewalk panels or when these sidewalk arches are actually put in. That's a sizable root system that essentially, if you think of the root system of a tree in a boulevard space as having sort of 4 sides to it, this is clearly 1/4 of that side of the tree. And so we wanted to know, essentially, if you do this to trees, how do the trees respond? Not the trees that die, but the trees that live, right? We already have some good research on the mortality of trees. And so we wanted to go about to try and figure out how to evaluate these trees. Now, there's lots of methods. People have come up with their own condition rating systems. Many municipalities have condition rating systems. And then there are formalized systems of appraisals and things like that have very strict protocols. But what we notice as we look through the research is that even a lot of these evaluation systems, if you compared between evaluators or even evaluators over time, you would find using the exact same system or formula that the values that they would get were different. So we wanted to know if there was an approach that we could use that was quantitative, so not as subjective as this, to see if we could actually rate trees and figure out what their actual response to these construction activities were. So being a tree ring person and wanting to understand tree growth from a quantitative perspective, this is an example of what we did. So I cored around 300 trees for this particular project, and this is an example here, the top tree and the bottom tree. These are different, but they're the same species, same size, and really only about 200 feet apart from each other. And by same size, I mean same height, same DBH, same crown spread, and roughly the same amount of twig elongation over the last few years. So this is the year 2012. These are both magnified at the same level, so it's an honest comparison of the size of these. And you can see that there's quite a bit of difference in growth. And just to give some more perspective, there's an additional 3 years of growth in the bottom. That tree on the bottom, even though it's the same size and by all the measurements that we usually use, is about the same as the one on top. Actually, if we look back in the records, had some construction damage. And this is 18 years post-construction. So you can see that reduction in growth continued on for quite a long time, even though the tree has survived. So this seemed like a reasonable approach. The trees that we looked at, the study took place in the cities of Minneapolis and St. Paul. I put this up so that people would have some understanding. We use residential streets, so trees growing in that grassy boulevard strip, not like the tree on the right-hand side where you can see it's in a more commercial area, no boulevard strip, just to make sure everybody's got that perspective. The research questions we wanted to go through were the impact of sidewalk construction on urban tree growth beyond condition rating. There have been several studies that looked at condition past construction damage, and those are available for other people to look at. We wanted to see how long it took trees to recover, if indeed they did recover. So we wanted to know how many years, basically, it took. And then we wanted to know how tree lawn or the boulevard width would impact the recovery of those particular trees. So a couple of indices, or a few indices we used. Basically, resistance, which is a year post-construction divided by the average growth pre-construction. And this is an index, so anything 1 or better is high resistance. We also looked at resilience, which was 5 years post divided by 5 years pre. And again, anything 1 or better is good resilience. And then we looked at recovery, which we looked at year by year afterward, so we could see how long it would actually take for trees to recover. So here's the results of this were essentially none of the 4 species that we looked at, which were basswood, Norway maple, hackberry, and honey locust. None of them had particularly good resistance. Basswood maybe a little bit, that's the tilia. And the basswood really did have some good resilience, but none of the other 3, really had much in terms of resilience. So how long did it take these trees to recover? They weren't particularly resistant or resilient to this. Basswood recovered the fastest. Really by year 2 it was recovering. In year 3 it was solidly recovered. Hackberry took about 4 years to recover to previous growth. So then by 5 it was certainly recovered. There was really no recovery over this 5-year period for either Norway maple or honey locust. And here the one thing I would add anecdotally that I noticed is that the honey locust trees, basically, they looked okay. So if we had used some sort of condition that would have maybe helped this out a little bit, Norway maple all pretty much looked not great after this period. If we look at recovery and boulevard width, we can see the differences here, so I'll just highlight the most dramatic results. So boulevards that were less than 4 feet in width or under 1.25 meters, there was no recovery of any of the species that we looked at in this study after 5 years. So that's not particularly promising. If we looked at the boulevards that were between 4 and 6, that was where we saw recovery really pretty good. And we didn't really have a lot of boulevards that were greater than 6 feet, although I think we would have seen better recovery if we'd have had basically a larger sample size there. Here you can see the Acer plantanoides, that's the Norway maple. There was really none of the trees recovered after 5 years. And we see that, but if we go down to just below that, the Gliditia triacanthos or G. triacanthos, which is honey locust, we can see that the ones on the wider boulevards actually did start to recover after 5 years. So that was promising for the honey locust. So, and that's sort of charts, I think, with what we read about and think about in terms of honey locusts when we think of being a tough tree and being fairly resilient. So then, now that we had some understanding that growth was actually impacted negatively, we wanted to see what the storm response of these trees were. So they were growing or some were recovering from growth. What did that do in terms of their stability? So in 2013, there was a storm that came through the Twin Cities. We had lots of rain in both the AM and the PM, and there were 2 distinct wind events, both in the AM and the PM. Okay. Gary Johnson and I were kind of walking around the city streets and looking around at trees, and we noticed that there was a lot of trees that were down. And we also started to notice that if we saw a tree down, it was a pretty good bet that or it seemed to us anyway, that there was a pretty good chance that the sidewalk had some recent construction activity. And by construction activity, I mean replacement, so new sidewalk panels. And in this photo, you can actually see the root severed there. That little surveyor's pin gives you an idea of the size of that particular root. And then this was actually a piece of pavement that had been curved around it, but again, that large section of root had been removed. And so we noticed this, and we wanted to see if we could set up a study to formally quantify and see if that was a significant finding or if that was just something we were seeing because we wanted to see that. So we worked with the city of Minneapolis, and we set up a formal study, and we looked at both damaged and undamaged trees. So we could see, well, some of the trees, and by damaged and undamaged, we wanted to be able to quantify, well, if the trees that had sidewalk construction but didn't fall down or vice versa. So we wanted to see how that impacted things. We ended up looking at just the street trees, over 3,000 trees, so quite a few in this particular study that was set up. The variables that we looked at tree species, DBH, stem girdling roots. The site variables were sidewalk and curb replacement within the last 5 years. So this was what we considered relatively new sidewalk replacement. And then we looked at if there was damage to sidewalk or curb, and then boulevard width, right? So another variable that the growth study. Then we also looked at some soil variables. We looked at soil texture, pH, and compaction, both at 6 inches and 12-inch depth. So the results of this, not surprising, I think, probably to anybody. Larger DBH, so bigger trees, had a higher probability of failure, regardless of anything else. So essentially, big trees fall down more in storms. I don't think that was surprising to anybody, and I think most of us have probably seen that. We also saw a higher probability of failure if there were trees plus sidewalk work. And that was sidewalk replacement work. Here you can see we're looking at the sidewalk edge of the root system, and you can kind of tell in the photo that those roots are severed fairly recently, and this is a newer panel of sidewalk, right? On this one, we see the same thing, but from the opposite perspective, where we see a tree has fallen, and we're looking at the curb side. And what I wanted to point out here is that on the curb side, we don't see roots that are jutting out into the street with the way the modern curbs are constructed and put into place. So we really see roots that hit that curb and then ride along so that they're more or less parallel with the street. All right, so this means that the roots that are severed on the sidewalk side, really, this is almost like a three-legged stool. And so by severing that third leg that goes under the sidewalk in order to repair the sidewalk, we think that that's what really happened to have a massive impact on the stability of these particular trees. So in terms of probability of failure, this is sort of rated that basswood had the highest probability of failure, which is interesting if you compare that with the fact that basswood also had the fastest recovery in terms of growth. So basswood seems to grow really quickly, and then and yet still has a higher probability of failure during these storms, right, from the same types of construction activity. That was then followed by the ash, maples, and elms. So really interesting in terms of the probability. So these would be the top four that had the highest probability of failure, all obviously large street trees. We also noticed an interaction between boulevard width and sidewalk repair. So essentially, the narrower the boulevard, the higher the probability. Same as with the construction, where the narrower the boulevard, the less likely of recovery. Here, the less stable it is, which just makes sense from a physics standpoint. You have less of a base there for the tree to remain stable with. To give an example of what this means in terms of the research we conducted, a 4-foot wide boulevard and sidewalk, you had about a 29% rate of failure. If you move that up, same species, to an 8-foot wide boulevard, the failure rate dropped by almost 15%. So really, that's a pretty big impact in terms of thinking about what boulevard width in and of itself actually does to the stability of those trees in conjunction with thinking about sidewalk construction. So if we look at soil characteristics, we didn't really find a lot here. Soil texture wasn't significant. Organic matter, not significant. pH was not significant in our findings. I don't know that we were too terribly surprised. Maybe a little bit on the soil texture. We kind of thought that might have more of an impact. Soil compaction did have an impact, but only at the 6-inch level was it significant. And I have this photo here. This is actually in Minneapolis of a boulevard that had been partially redone for curb and new sidewalk, and this is to kind of maybe highlight what might be going on here. Now, we didn't do any excavation of the soil. We just did tests of the soil compaction, and so, but you can see that it's not, you know, when I watched them refill this hole, it was filled on top of. There wasn't a lot of excavating out this material that was underneath, and so there isn't, it's not going much past 6 inches here, and so it could be, and from what we saw from a lot of the root plates, the roots weren't going really that much further beyond 6 inches to a foot in some of these boulevard spaces, so you'd see this pretty flat root system. So severance of that flat system kind of making that three-legged stool even flatter. So very interesting. So how can we predict and prevent some of these issues? So some of the research that actually has been done on human stability in terms of walking, so the average person that is able-bodied, that is walking on a flat surface, is destabilized if there's a change in grade of up to 1 inch. So at 1 inch, people start to trip, essentially. Trip fall hazards start to happen. So here you can see this pin oak has a sidewalk here, and this pin oak is not very big, right? It's only about a 12-inch diameter pin oak, and it's already starting to sort of move that sidewalk slab. So this is actually working somewhat with Larry Costello's work, sort of expanding on this, some of the work that he had done in the early 2000s, I believe. We started to do trunk flare diameter predictions, and using that in the paper that highlights how this research was conducted is there at the bottom of the screen if you're interested. But essentially using this predictions, we were able to give some recommendations as to the boulevard width in feet. And you can see that at 8 feet is about the minimum recommended boulevard width. And those of you that are groaning and saying that doesn't seem very reasonable, I would agree, and so we'll give some other potential solutions as to how to deal with that. But this essentially was based on our research and then a lot of other research that basically says you need to maintain this distance so that you don't have infrastructure disruption, which facilitates the need for sidewalk construction, which then has a probability of damaging and disrupting those trees. So species selection, I know this is no news to anybody, is very important. Neither of these two species, there's a pin oak and there are maples, so pin oak on the left and maples on the right. These are not long-term solutions in terms of species. The one on the left is about 12 inches diameter, and it's already causing sidewalk disruption, which, depending upon how the sidewalk is repaired or how that is dealt with, that could mean less stability for that particular tree. In the maple, that's less than a 2-foot wide boulevard. Obviously, those trees are not planted for the long term in that particular situation. Here, though, we do have a large American elm, and I would hate to tell anybody that you have to cut that down just because it lifted the sidewalk. And so you can see the sidewalk has been shaved. And in communities that I've talked to, I haven't seen research on this specifically, but sidewalk shaving is essentially just removing that lip. So you come down with a sidewalk grinder. There are different systems that do this. And the people that I've talked to that have employed this in their communities or on their campuses say that this lasts about 7 to 8 years is how long they get, and depending upon how much needs to be shaved off, sometimes they can do a couple of treatments of this at a cost of $75 to $200, at least in the Twin Cities of Minnesota. So really here you have zero root damage, and you eliminate what you need to eliminate, which is the trip fall hazard. Ramping, this is actually, that's my helmet again. There's a root from actually the champion red mulberry in Minneapolis, and you can see that its root is diving underneath the system here, the sidewalk, and you can see it's been ramped, and I biked and walked over this particular path thousands of times and without really noticing it. So ramping, while not particularly aesthetically attractive, does seem to be at least a functional way to deal with that without disrupting the root system. Curving and narrowing of sidewalks. So there is the possibility of curving, although kind of watch that if you can curve and narrow without disrupting the root system, right? This means the sidewalk before and after is wider, which is nice for people to pass through, but it actually does allow you to narrow it just at the tree to avoid or minimize impacting the tree's stability. Flexible materials, I haven't used or seen used, although I've read about some of the flexible materials that you can actually use as sidewalks that actually flex and move so that they don't create those little bumps, but they do allow for kind of a flexible change in grade. Here it was just used as rocks, which is probably not going to be ADA compliant in most communities, but is preferable to severing the tree roots. If you can't do anything, tree removal is probably one of the better things to really look at in terms of the stability of the tree and its potential negative impact to people's homes, cars, and in the worst case, people's lives. Repairs, so we did a little bit, nothing formal, but I've looked through some of the data to look at the repairs. Here you can see this repair. This happened to be in front of my house in Minneapolis when I was living there, and I kind of watched this repair. It lasted about 2 years before it lifted to over 1 inch, right, which is the threshold for trip fall hazard, so that's interesting. And if I comb back through the data, of the 60% of the repaired sidewalks, so where the sidewalks had been actually replaced, additional repairs, meaning they'd been lifted with over that to that inch or over that inch, were needed within 7 years, and that's only because that's when we had the data. So some of them likely needed repairs sooner than 7 years, but we at least know within that set. So some significant findings. Sidewalk replacement, 2.25 times higher probability of failure, right? Wider boulevards are better. Species selection is critical. Root severance definitely reduces growth and likely also reduces condition for a number of species. Root severance reduces the stability for up to 5 years after, and possibly longer, but we only looked at that 5-year period. And sidewalk repair solutions that don't require root severance are obviously favored. And remove the tree if root severance is completely unavoidable is a reasonable thing to consider at that point. I just want to acknowledge and thank, obviously, Professor Gary Johnson and Chad Giblin, both at the University of Minnesota. I worked with them for a number of years, and they were kind enough to share the data that we used for this study, and Philip Pachandi, and actually everybody at Minneapolis and Park and Recreation Board who really helped us with the storm damage study, and of course the City of St. Paul, who helped with any of the construction studies and allowed me to study those trees. So thank you very much.